Okay guys, in this segment here, what we're going to do is go back to our lab data from our range versus angle lab and talk about that launcher that we had and kind of what other things can we figure out by launching something at an angle, okay? So one thing we want to take a look at is we have the known velocity of our launcher, okay? Most of our launches at the second setting, we're shooting somewhere around 4.5 meters per second, something in that setting, okay? So we should be able to calculate theoretical values of that whole trajectory from our lab yesterday. All right. Now that being said, we want to focus in on one angle. So we're going to talk about the 60-degree angle only for these problems, but you could do this for any angle that we shot this thing off at. Okay. So first thing we want to do is when you shot this sphere at 60-degree angle, what were the x and y components of that initial launch velocity? All right. So if we go back to that problem, if you remember, we had an angle of 60 degrees. And our velocity initial, or the launcher, that would be our VI. I'm just going to say it was 4.2 meters per second. I don't know the exact velocity of your launchers, but that would be close enough for us. Okay. What we want to know is what is the component, right? We want to know what's the x component and what is the y component. So what we're solving for now is that Vx and that Vyi. To do that, let's do a quick little diagram. So we know that we launched in the x direction and the y direction, and that kind of creates a triangle for us. Okay, we know that the x direction would be our Vx, the y direction would be our Vy initial in this case. So we don't know those two things. We do know that the angle is 60 degrees, and we do know that the velocity resultant, or the overall velocity shot at, was 4.2 meters per second. This is where you would put in your particular launcher's velocity in here. I'm using 4.2, okay? From this, if you take a look, well, I know an angle, I know the hypotenuse, I need my components, okay? So with using that, I can use SOHCAHTOA to solve this. Now, I don't have opposite and adjacent, so I can't use the TOA part, but I can use the SO and the KA to make this happen. So I know that the sine of 60 degrees now will equal opposite over my hypotenuse. All right, well, my hypotenuse is 4.2, so I can say that the sine of 60 degrees times 4.2 meters per second will equal my opposite. And opposite, in this case, we look over here, opposite was my velocity in the y direction. So that equals my Vyi. I can do the same thing for cosine of 60 degrees now times 4.2 meters per second. Okay, that will equal my adjacent because the KA is adjacent. So the adjacent is my Vx. So that will equal my Vx. Okay, if I plug those numbers in and I solve for that, I find that my velocity in the y direction initial is equal to 3.64 meters per second by plugging that into my calculator. Make sure you're in degree mode if you are a student who has calculus or even pre-calc, because sometimes you guys do radians. Okay, so my velocity in the y direction is 3.64 meters per second. So I'm going to put that in up here is 3.64 meters per second. So I know my initial velocity. Cosine 60 times 4.2 gives me 2.1. So my velocity in the x direction is 2.1 meters per second. So if I put that into the calculator, that's what I would get for that part. So now my Vx is 2.1 meters per second. Okay, so that's our starting point. All right, so now we know everything about the initial launch. All right, that's the last time I can use this triangle. Okay, unless I'm going to get some information about the end or some instantaneous point in time, I cannot use a triangle anymore past this point because everything else is along that parabolic path or that trajectory from going from here on out. All right, so moving down, the next question asks for is what is the maximum height? So we want to know what is delta y maximum. That's the next thing it asks us for. Okay. Well, let's take a look. If we diagram this out kind of quickly, we launched it, came down to here, and launched from here. Okay, we have a maximum height halfway through my travel. Okay, we know that when delta y equals a maximum, that our velocity in the y direction final is 0. Okay. We also know that that's half the time of the total flight. So these are things that we know about this maximum position up here that will become useful for us as we move forward. Well, if I know velocity final is 0, and I know my initial velocity in the y direction was 3.64, by knowing those two things, I can find an equation, and I can actually solve for this. So let's go back to our equations now. And if we look, to find delta y, if I know velocity final, I know velocity initial, and I know g, I can use this bottom equation here to find my delta y. Okay, so that's what we're going to do. We know that velocity final in the y direction squared equals velocity initial in the y direction squared plus 2g delta y. Oop, that's a y. Okay, so velocity final in the y direction squared minus velocity initial y direction squared, okay, would equal 2g delta y. If I rearrange this, I now can divide both sides by 2g, and if I do that, that cancels out, and what I get is that my velocity final squared minus my velocity initial squared, 2g, equals my delta y. All right. Now, velocity y final, well, that's 0. So I ended up getting a negative, and velocity initial is 3.64 squared. Make sure that you keep the negative outside. So this is outside of those parentheses because it's not a negative 3.64. It is minus 3.64 squared. That's a problem we sometimes see happening. Divided by 2 times a negative 9.81. We want this because we want delta y to be positive here as we do this. Okay, this is in meters per second squared because it's being a squared value. This is in meters per second squared. So second squared will cancel out. One of these meters will cancel out, and I'll end up with meters as my label here to solve for delta y. Okay. Now, if I plug that into the formula and actually solve it, it ends up being that delta y then equals 0.675 meters. Okay, so I got to plug this stuff into my calculator, and I get that delta y. Okay, so at the maximum height, so delta y max is 0.67 meters high. Okay, that's what we get there for that one. That's our first one. How long did it take? Is our second question is how long did it take to reach the maximum height? All right, so now we want time. So we know, if we go back to our diagram, okay, that at the maximum height, velocity y is final is 0, and we know it's half the total flight time. So that gives us some options of how we want to solve it. I'm going to tackle it from the point that my velocity in the y direction final is still equaling 0. My velocity in the y direction initial is still that 3.64 meters per second. I think that is going to be my easiest way to solve it. I have the equation that velocity yf equals velocity y initial plus g delta t. So I can find t pretty easy here. Okay, so velocity y final minus velocity y initial divided by g, then will give me my delta. That's my delta. Holy crap, that's bad. My delta t. Okay. Again, this is 0, so I end up getting a negative 3.64 meters per second divided by a negative 9.81 meters per second squared. Meters cancels. One of my seconds over here cancels. I have seconds in the denominator twice, which means it's actually in the numerator, so my answer is going to be in seconds. And if I take my 3.64 divided by my 9.81 and I solve for that, I end up getting 0.742 seconds. So that is, oh, nope, that's not true. I lied. That's my answer to our next one. Yes, I did pre-work all these out. So that way I didn't have to punch things in the calculator. If I do that, that's going to equal 0.371 seconds for my time here. So my time is going to be 0.371 seconds. Okay. Again, that is to get me to the top, right? So this is at the top point is 0.371 seconds here. Okay. Not the whole way, just to the top. All right. So that is time at the max height is what we get here. The beauty is this. The next question asks how long it was in the air, assuming it lands at the same height it was launched. So if it lands the exact same height it's launched and it was half the time, all I need to do is double my initial time here. So in this case, if I take my 0.371 seconds times 2, that will tell me what I get when it lands, which would be 0.742 seconds. So my total flight time is 0.742 seconds of my flight there. Okay? Lots of math here, but each one of these things is progressive in terms of what we know, as long as we know our equations and can apply the different variables as we go through this. Okay? Next question asks us, how far away from the launcher did it land? Okay, so now we need to figure out, well, where is my delta x? Okay, going back up to my diagram that I drew, I want to know from here all the way to here, what is delta x? Okay, for me to find delta x, I need to know how long it's in the air, which I already know, right? I know how long it's in the air, so that is right here. And I need to know how fast it's moving in the x direction. So if I go back up, do I know how fast it's moving in the x direction? Yeah, that's the very first thing when I solved for, way back here. So I know that also. So that's going to make my life really easy. We know that the delta x is equal to the velocity in the x direction times my change in time. Well, Vx was 2.1 meters per second. We solved for that previously. My time we just solved for, so that's times 0.742 seconds. And meters per second times seconds cancels, so we end up with the meters as my label. So delta x equals this, which would equal 1.5 meters. Okay, it's like 1.48 something, something, something. But because I only have 2 sig figs here, I'm going to leave it to only having 2 sig figs. Ooh, look at that. I didn't mean that. Okay. So we end up with 1.5 meters is my delta x in this case. All right. So we have lots of information about this launcher that we could do pretty quickly if we just know our equations and pick those out. Now, obviously, I do this very fast because I've also worked the problem out previously, and I'm pretty comfortable with all my equations and my variables. So it will take you longer to do these, but they're all solvable if we attack it from the standpoint of what is my x direction, what is my y direction. I gotta have time. Okay, time is my biggest thing. I need to have time to get between x and y in terms of my variables, and then we can do that. Okay. Now there is a bonus question right here. At what horizontal position was a sphere at a height of 0.15 meters? I'm going to solve that for you in a separate video lesson because this is a little bit more mathematically than we would probably ask you come assessment time. So we're going to end the video here. Thank you.